as mentioned, I'm going to demonstrate the influence, actually the positive influence of using yielding elements in tunnel construction. And also in the tunnel during the excavation and construction, and also in long term, also the impact that it may have in the safety of the tunnel under the rock masses with high squeezing behavior and also high overburden, which in our case is about almost 900 meters. I will explain later what is the concept of squeezing and why the tunnel designer is one of the concerns for tunnel designers. The geometry and validation is with respect to Tauern Tunnel in Austria. Let me introduce myself shortly, and then we will continue with the project. I'm Negar Zamani. I have studied civil engineering in Iran, and in 2016, I have decided to continue my study, my master in Ruhr University Bochum in Germany, in field of computational engineering, which has linked me to the concept of finite element method, continuum mechanics, and their implementation in construction engineering, as well as geotechnique also. So that I have decided to investigate the installation of yielding elements in tunnel lining segments because I found the modeling of these elements so challenging. Although they are used in the tunnel construction so often, but so far there is not a proper way to model these elements and their damping behavior in the tunnel lining. I have divided the presentation into 4 main parts. First, I will introduce you the squeezing behavior. Then we will show different types of yielding elements that are used in the market. Then I will let you know the material properties that I have used for different parts of the tunnel and also the support system. Then we will see the results that we carried out from DIANA 3D model. One of the concerns in conventional tunneling is defined by the International Society of Rock Mechanics as a time-dependent large deformation occurring around a cavity, which is a tunnel in our case. And the consequence of this high unsymmetrical deformation is overstressing of tunnel lining, and it may lead to failure and it damages the safety of the tunnel. In this slide, the pattern of deformation in the rock mass surrounding an advancing tunnel is shown. As is shown, the radial displacement reaches to its final value at about 1 1/2 tunnel diameter behind the tunnel face. It is a schematic of the tunnel deformation so that the tunnel designers can estimate how the tunnel and during the excavation where they should be worried about and stop the deformation. In order to analyze the movement of the tunnel wall and its face on the variety of squeezing range, since we don't have just, we have many types of rock mass with different types of squeezing behavior, so that the tunnel designers need a way to estimate how it will be happen, how much we should concern about the support system of the tunnel. So in this pattern, an estimation system is modified by Professor Hook in 2001 and is the curve of tunnel strain versus the ratio of rock mass strength to in situ stress. I would say it satisfies the need for tunnel stability predictions. So it's really it has been used very much, and it's a real good way to estimate the tunnel movement. Now to reach to the passive support system classification, and before that, I would say in general, support systems are divided to active, which stops any movement, and passive, which allows controllable deformation. And regarding to the deformation approach, are classified to radially and tangential. Yielding elements also deform, as is shown here. Yielding elements also deform as tangentially. However, they can apply this deformation by means of two sliding parts on each other, which we mostly see in mining industry, not in tunnel industry, and by means of compression. Most yielding elements in the market and for tunnels with 6 to 10 spans are in compression branch and made of steel or concrete. In next slide, I will introduce you these three types of yielding elements one by one. First, we go to the high deformable concrete. It is developed by Shotcrete company and is composed of a high strength concrete with porous aggregate matrix like gypsum or glass foam particles, so that it exhibits damping behavior. The load deformation behavior can be controlled by making modifications in the geometry or also by changing the material composition. It is not still a mass product, but they can be used in mechanized tunnel as well, and the efficiency of the lining will increase significantly. LSC yielding elements or lining stress controllers are consisting of a group of yielding steel tubes fixed at the top and bottom by means of two rigid plates. The outward movement of these tubes can be controlled also by the outer tubes as shown here. But I would say a shortage for this type of yielding elements is like as high deformable concrete is it has almost high initial stiffness, and for yielding elements that would be better if this initial stiffness is less and the load bearing acts in less forces, not for example in 1000 kilonewtons. Latest development leads to improving new yielding elements as a combination of steel and porous materials. The shortcoming of the porous cement-based elements are relatively high initial stiffness. However, is almost found in this combination of sealers with different properties that aid in achieving the optimized load deformation curve. So we have a steel tube, and the sealers of different types of porous cement can be sealed tubes, and they will act together so that, as we see, the initial stiffness is more or less, and the load bearing capacity is very good, I think. Body using elements consist of some circular hollow tube profiles that are connected in layers by means of intermediate plates or sometimes bars. As shown in the graph, it has a relatively quick, low bearing capacity at a small compression. So that was the result. I have decided to use Bobby yielding elements in my project, and I carried out the E-modulus from this curve, and I applied to the springs that I have modeled instead of the yielding elements. I will show you later how I defined the yielding elements, but I wanted to shortly describe you why I decided to use these elements. And they are actually mass product in comparison with the new LSC, which was a composite of cement and steel. This is a wave shape of this water yielding elements, and can be used also in future maybe, or I don't know if already is used in a project or not, but so far I know they're not mass product as high deformable concrete in mechanized tunnels, but that would be a good idea. Now we reach to the point that I will show you how I model different parts of the tunnel, consisting of the shotcrete, yielding elements, rock mass, rock bolts, and so on. In DIANA, we have this opportunity to model the yielding elements. At least I figured out in two ways I can model the yielding elements. First, I decided to use the interface. So between two parts of the tunnel lining segments, I applied interface to model this capacity of deforming. But actually, I didn't find the results that it didn't satisfy my exceptions. So I decided to use the nodal springs, which was really successful, and I provide you to use them first. We have this opportunity to apply the inputs of the springs as a forced elongation of the spring manually. I have done it also. And as you see, we have a multilinear behavior of the spring. I had to put the initial stiffness for the spring also. First, I thought, okay, it's the initial stiffness, so I have to get the slope of the first line and put it in the input. But the fact is, in tunnel construction, when we have the shotcretes, when they are fresh, they don't have a high stiffness. So, and when the force is applied on the tunnel, I prefer to transfer this force to the yielding element first instead of the shotcrete, so that I stop the shotcrete failure. So if the yielding elements should be designed in a way that their initial stiffness shouldn't be that much higher than the fresh shotcrete. So I carried out the second line step as the initial stiffness, and I put it in the initial stiffness of the spring. Here is the way that I have modeled the tunnel segment. It's a part of the top of the tunnel. The tunnel is about 60 meters and 80, meter. Each of these plates, these 3D curved plates, are 1 meter in elongation, and the nodal springs are applied in distance of 1 meter. You may ask why we have a gap here. You could also don't have this gap and apply interface, as I mentioned, or also spring, it's no matter. But that was more similar to the reality. So I thought maybe that would be better if I have a gap between the segments and apply the yielding element. Look, here is the tongue segment, is from the tower tunnel document, and we have one pair of yielding elements in the sense of 7 meters. And the excavation is in 3 parts of top bench and inverse of the tunnel, and we have 23 rock walls around the tunnel section. And this is the way how I modeled the tunnel segment. It is a 1 meter section. This is also another view for the 80 meter, and I have divided the soil inside the tunnel to 3 parts so that I could excavate exactly the way that in the reality is excavated. This is how I applied a cube around the tunnel to have more fine mesh, to have more precise results. And that would be better if you don't apply this fine mesh in all the rock mass, in all the cubes, which is about 100 meters in 100 meters. So the calculations would be so confused. This is also view of the model. It's a cube of 110 to 100 and with overburden of 905 meters, but here it's just 55 meters is considered, and the rest of that is applied as a distributed load at the up of the tunnel, at the up of the rock mass around the tunnel, with use of this formula and the density of the rock mass and the height up to the tunnel top. These are the parameters for the rock mass. The way I have decided to model the rock mass is hook brown. Since I had the parameters for the turn tunnel for the hook brown, so I have model. You can also use mock clump, but you have to consider the creepy behavior of the load. For more investigations, I tried to use 2 different elastic metals of the rock mass. One is 1.76 gigapascal, and the other is 3.65 gigapascal, to figure out how the rock will affect the performance of the yielding elements. I mean, if it is more stiff, then how much less we have deformation. And the in situ stress is proved by the first phase output that we see that it's exactly what we assumed. About the shotcrete, how we model the shotcrete. The shotcrete is carried out, so the elastic models of the shotcrete is carried out from the data of the laboratory of tunnel construction chair of my university, Royal University of Brooklyn. And but the way that I modeled that in the DIANA was a linear elastic model. Since I wanted to prevent any complication in the model, so I decided to have 4 different linear elastic models, and I gradually increased the in-modulus to 1, 3, 3, 6, and 28 at the end of the shotcrete age, with respect to the ratio of excavation rate. I mean, we excavate, and the document says that the excavation of the top is 3 meters in a day, and the bench is 6 meters in a day. This is the shotcrete segment, the 3D curved shells in the DIANA, and I would say they present the behavior of the shotcrete in a precise way with the material of concrete and nickel. The construction and the excavation of the tunnel is a phase construction. So in this model, I have defined 60 phases, and we start the top with rate of 1 meter. Then when in the specific point, which I have defined here at the 10 meter far from the face of the tunnel, when the settlement of this specific point is stopped, or at least doesn't change so significantly after phase, then I start to excavate the bench with rate of 2 meters. So with the, with the excavation stage of 2 meters, and it started in the 31 phase, and then we will continue with excavating the inverse as well till end of the tunnel, which is 60 meters. Now we're to the results. We will see how are the results and what kind of impacts they had. So in case of using yielding elements and not using yielding elements, and in case of the rock mass with D modulus are 1.76 or 3.65. This is the stress distribution of the case that we have no yielding elements. As we see, I can see because this panel is beside. As we see in the next slide, so keep it in your mind, then we will make the comparison in the next slide, that how in the case of using yielding elements, the stresses are dispersed and also reduced. So it is the most valuable result that we have, that the stresses on the walls and top of the shotcrete on the tunnel lining is decreased, and it's really valuable since it prevents any failure and collapse of the tunnel. For the vertical displacement, first I considered a model which no tunnel lining. I wanted to see if I have no tunnel lining, how much this intact rock settle. And it's about 16 centimeters. Now, in case of having not having yielding elements, in the right hand, we have the case with yielding elements, which we see is 13 centimeters. And in the left hand, in the case of don't using any yielding elements, we have 12 centimeters. So 1 centimeter more in case of using yielding. That's good. And when the rock mass is more steep, this difference is about half centimeter, since the rock mass is also more steep. But we still have the deformation, the higher deformation, vertical deformation in case of using yielding elements. This is another view of the yielding elements, and as we see in the inverse of the tunnel, because of the spelling, we have also upward movement, but it's normal, and in our cases it happens. The distribution of vertical displacement is shown here, and I have zoomed a little bit since I wanted to show you how the yielding elements absorb the vertical displacement themselves and doesn't let them to transferred to the wall of the tunnel. So they absorb them into these lines, these blue lines. They are the yielding elements, and they absorb the vertical displacement. This is the graph of the results as what we have already seen in case of two different types of rock mass, more stiff and more soft, and with and without yielding elements. See the difference. About the rock walls, as it's shown here, in case of using the yielding elements and not using the yielding elements, the maximum quantity of stresses, compression is decreased. At the end, I want to let you know that although DIANA was really helpful to model the yielding elements, and I got really reliable results, and as expected, actually. However, we need still material types which can be modified by the users. I mean, we can also modify material for the yielding elements specifically to consider all the behaviors of the yielding elements, like rotational buckling and the post-buckling process, and not just the elongation and the vertical displacement of these elements, actual displacement. It's really fine for these steps. At least we can prove that they have such a positive influence in tunnel construction and industry. However, we need still to develop a material that can present itself the yielding elements, and we can modify it whenever we change the material of yielding elements, and then reach to the most optimized material for the yielding elements, and then having the mass product of them. Thank you for your attention, and you can mail me in the future your results, your concerns, and also share me any valuable results that you got. Share me, I will be so happy, and I'm here to answer your questions if you have them.